Hello, everyone. Today we're diving into the fascinating world of integral calculus and its real-world application in making a helmet. At its core, integral calculus is a tool that helps us find the total accumulation of quantities that continuously change. Imagine you're examining a curve. Rather than looking at the curve as a whole, you zoom in, focusing on each infinitesimally small section of it. You then add up all those tiny bits and voila, you've got your whole curve. In essence, integral calculus is like a mathematical microscope, allowing us to examine and sum up these infinitely tiny pieces to comprehend the whole. So, whether it's calculating the area under a curve or determining the total surface area of a helmet, integral calculus plays a pivotal role. Think of integral calculus as a way to sum up infinitely small pieces to determine a whole. Now, let's apply integral calculus to the surface area of an object. For our example, we'll consider a cylindrical helmet. Picture it, a sleek helmet shaped like a perfect cylinder. But how do we calculate its surface area? Well, the formula for the surface area of a cylinder involves integrating over its dimensions. Here's where integral calculus steps in, a hero with a cape ready to save the day. You see, integral calculus allows us to sum up infinitely small pieces to determine a whole. It's like being handed a puzzle, and piece by piece, you start to see the whole image. In the case of our helmet, we're integrating over the radius, height, and the angle around the cylinder. Each of these dimensions is a puzzle piece, and integrating over them gives us the complete picture, the total surface area of the helmet. We're integrating over the radius, height, and the angle around the cylinder. The integral looks complex, but let's break it down. At its core, the formula is composed of two key pieces: the 2 pi r squared term and the 2 pi r h term. The first piece, 2 pi r squared, is a familiar friend. It represents the lateral surface area of the cylindrical shell. Imagine you're looking at the helmet from the side. This term accounts for that entire curved surface you see. The second piece, 2 pi r h, represents the circular top and bottom surfaces. Picture the top of the helmet and the part that cradles the back of your head. That's what this term is accounting for. But we're not just looking at one static size of helmet. We need to account for the variations in radius, height, and angle. That's where the magic of the triple integral comes in. It sums up all the infinitesimally small surface elements. The triple integral accounts for variations in radius, height, and angle, summing up all the infinitesimally small surface elements. Now, imagine we're making a cylindrical helmet. Integral calculus becomes our secret weapon in this process. Here's how. It aids in calculating the total surface area of the helmet. Why is this important, you ask? Well, knowing the surface area is absolutely crucial for determining the exact amount of material we'll need to construct the helmet, but it doesn't stop there. When we integrate over the dimensions of the helmet, we're not just adding up flat surface areas. No, we're summing up all the surface areas, each infinitesimally small, but together accounting for the curvature and contours of the helmet. This is how integral calculus allows us to capture the true shape of the helmet in our calculations. By doing so, we can ensure that every inch of material is accounted for, leaving no room for wastage or shortage. This precision ensures an accurate estimation of materials required in the manufacturing process. In conclusion, integral calculus isn't just an abstract concept confined to textbooks. It's a powerful tool with real-world applications. This mathematical marvel is like a master key, unlocking the door to understanding complex phenomena in the world around us. It gives us the ability to sum up infinitely small pieces to form a whole, which proves invaluable when applied to the surface area of objects, such as our example of a cylindrical helmet. With integral calculus, we can calculate the total surface area of the helmet, a crucial step for determining the amount of material needed. This precision is the secret sauce to optimizing material usage, streamlining manufacturing processes, and creating safer, more efficient products. So, the next time you put on a helmet, remember the integral calculus that went into making it a perfect fit for your safety. Thank you for exploring the math behind the helmet with me today. Let's bring this concept to life with an example. In this scenario, imagine yourself placed into the shoes of an architect. Not just any architect, but one who is given the unique challenge of designing a spiral elevator for an upcoming state-of-the-art high-rise building meant to punctuate the skyline of a bustling city. The building, with its innovative design and aesthetic appeal, stands an impressive 200 feet tall, a magnificent structure touching the sky. Now, coming to your task, the design specifics of the elevator are intriguing. The radius of the spiral is designed to increase by 1 foot for every 10 feet of vertical height. This is an unusual but interesting design characteristic that adds an extra layer of complexity to your task. You see, each spiral twist and turn adds to the total length of the path the elevator will traverse, and this necessitates a deeper understanding of mathematical concepts. To help in our calculations, we bring in the help of an important mathematical tool, the integral function. The integral function, which we discussed earlier, is going to be our guiding light in this complex calculation. It offers us an elegant way to compute the total length of the spiral path that the elevator will follow from the base to the pinnacle of the building. Now, let's get down to the business of plugging in the numbers. We apply the specifics of our building and elevator design into the integral function. We integrate, keeping in mind the increase in radius with the increase in height. As we compute, we find that the total length of the spiral path is surprisingly long. We arrive at an astonishing figure of approximately 636.6 feet. This figure represents the precise distance that the elevator will travel from the bottom to the top of the building. Understanding length is not just about numbers. It's about the practical implications it carries. It informs the amount of rail that will be needed for the elevator to journey along. This in turn, the cost, the sourcing, and the installation process of these rails. Furthermore, it helps in calculating the time the elevator will take to reach the top floor, a crucial metric in evaluating the efficiency of the elevator. This information is indispensable for engineers when determining the power required for the elevator motor. Too little power, and the elevator won't reach the top. Too much, and it's in use of energy. This example that we have discussed today is just one of many ways in which integral calculus plays a vital role in designing efficient and functional structures in our day-to-day world. The seemingly abstract concept of integral calculus finds meaningful application in the concrete world of architecture and design. The bridge between the world mathematics and the world of practical engineering is built on such crucial concepts. So, the next time you find yourself in a spiral elevator, soaring to the top of a high-rise building, take a moment to remember the integral calculus that went into making your journey possible. Think of the complex calculations, the careful and the ingenious design that allows you to ascend with such ease and efficiency. Thank you for joining me on this mathematical journey.